Hello. Can everyone hear me? Yay. I'm Tess, and I'm maybe a little bit more excited about algorithms than the next person. Who here is super interested in algorithms? Otherwise, this might not be the talk for you, to be honest. I'm so interested in algorithms that over the last year, I should probably have joined something like Algorithms Anonymous or something. I've done daily leet code for a year, entered in competitive programming and a few other things, but it also made me go down this path of actually looking at what these algorithms are and look at the base of them. Because I kind of am so old that I forgot everything I learned in school about these algorithms. They have gotten a little bit of a bad reputation, I think, as something that we're only using in interviews for big tech firms. I disagree with this statement a little bit because I do think that while my job at Microsoft does not look like this, not at all, I wish it did. I actually really wish it did. But it does look a little bit like this. So it looks like I have to make algorithms that does background removal or that does color decomposition. Or right now I'm working in C# scheduling and orchestrating very large sets of jobs on batch. And this too requires these algorithms. So the things that I've learned in these base algorithms make me make better choices for when I create the bigger style algorithms. We're going to go through a number of algorithms. And we're going to start with a very, very simple one that I think most of you know. And if you don't, you will know it in 5 minutes. So we have a situation where I'm thinking about a number between 1 and 100. And you're going to guess what number it is in the least questions possible. I will always tell you if it's higher or lower. What would be your optimal first choice, first pick? Anyone? 50. Everyone knows. Why would it be 50? Whoever said it.
Gives you the most information.
Yes. It essentially reduces the set of numbers that we'll end up with by half. In fact, it's probably not the most probable number. The most probable number would probably be 7, 42, or 69. But it will definitely remove the most amount of numbers. So we're doing this. And then I say higher. And someone picks now we're dividing the next set in half. And the next, and the next, and the next, and the next. And finally, we end up with only one number. And it happens to be 85. So we did this in 7 tries. And this is actually the maximum number of tries we would ever have to guess for 100 numbers. This algorithm is called binary search. And it's a very basic but very useful algorithm, as we'll see. In fact, in this case, if we would have guessed 1, 2, 3, 4, 5, and so on, we would have had to guess 85 times. That's a little bit of a waste of time. Maximum, we would have guessed 100 times if I would have picked 100 and you would have gone linearly. As compared, so this is called O of n. We'll get there later. As compared to with binary search, where we only had to guess 7 times. This is also called O log of n, if anyone is interested. And the reason for this is because when we're constantly dividing, we're actually doing it in log 2 times, so which is 6.64, but you can't do 6.64 guesses, so it's going to be 7. Now, you might say, okay, so 7, 85, who cares? Computers are fast. It's not going to matter. But if we're talking about a million numbers, now we're talking about, instead of 7 guesses, we're talking about 20 guesses versus a million. And if we're talking about 1 trillion numbers, we actually have to guess only 29 times instead of 1 trillion. And that's where it starts making sense to use these kind of algorithms. Now we can use these algorithms to find an item in a list, because this is if the list is sorted, We can find the item in the list in the same way. We would go from the ends, pick the middle number, and then say, is it higher or lower? It's lower. Now we shorten our space to this. And this is like a typical use case of binary search. In Python, so I spend most of my work time in C# and most of my free time in Python. In Python, there is a bisect function for this. So you don't even have to learn how to implement binary search. You can just use the predefined function. But we can also use it in some other, a little bit more interesting cases. So this is a case, there's a leet code problem, but it's actually a leet code problem that kind of depicts another bigger problem. It's called Coco eating bananas. So what this is about is this. You have Coco, who's a monkey. She likes bananas. And her handlers give her piles of bananas. Each pile contains a different number of items. They say, you need to eat this up, or she wants to eat them up, but they have to be gone by 8, or in 8 hours. She has this thing where she will only ever eat out of one pile every given hour, and she wants to savor the banana, so she wants to go slow. So basically, what's the slowest speed that we can eat from all the piles and still make it in 8 hours? If we do this, is calculating this, if we go 1 banana per hour, then it will take 27 hours. That's obviously too high. 2 bananas per hour at 15 hours, 3, 4. So 4 bananas per hour is the lowest number of, lowest speed we can go at and still eat all of these. So this is now, we're doing a linear search. And that's fine. But what if it turns out that Coco is a little bit of a different type of monkey? And she eats not only 3 and 4 bananas, but they give her 10,000 piles of bananas containing 1 trillion bananas, or what is it, 1 billion bananas in each pile. Now, we might not be talking about monkeys and bananas anymore, to be honest. We're talking about like maybe Azure batch jobs, I don't know. Because the numbers here are totally bananas. But what do we do about this? Because if we go through and we do this linear search, we'll see here that the highest speed that makes any sense is the speed at which we eat like a full, like the biggest stack in 1 hour. So in this case, the biggest stack is 11. So we'll eat it at 11 bananas per hour. Anything above that will still achieve the same number, 4 hours, right? But if we're now talking about 10,000 piles and 1 billion bananas per time, we're now talking about 10,000 times 1 billion, which turns out to be like 10 trillion. And that will, I don't know what your hardware looks like, but my hardware cannot calculate this. So what can we do then? Well, we can use our binary search. So we can calculate sort of like every single one of these rows. We start at the bottom and top. We'll take the middle piece, which happens to here be 5 billion, and see, is this good enough? If so, we can move to lower. If it's not good enough, we'll move at a higher speed. So this is a way that we can use binary search even in a set where it's not an array and it's not a set of numbers. As long as it's some sorted kind of area where you can always answer, is it lower or higher? Am I good enough, or which direction should I move? So, and now we've turned it into, instead of 10,000 by 1 billion, it's like actually 290,000, which my hardware very much can handle. So we saw, so this is like the first of the important algorithms, I think. I talked about like O log n and O of n. I'm sure most of you know of big O notation. I'm not going to spend a whole lot of time on it. I'm just going to do like a 1-slide primer for anyone who doesn't. So big O notation is a way for you to compare algorithms. It's a very crude yardstick to measure things by. It's not at all, it won't tell you the actual performance of an algorithm, but it will tell you kind of like the relative to maybe another algorithm. So if we have a list of fruits, then if you go through and you go through that list and you print out everything, that's called O of n, because that's like linearly relative to how many items you have in the list. If you do something like you go through in a nested loop, it's going to be O of n squared, because now you're having to do like n times n operations. If you're just printing out like a random number, even if you're printing out like 5 random things or 100 random things, that's going to be called O of 1. We don't care about constants, so it's not going to be O of 100, it's going to be O of 1. If we do a binary search, we've already seen that that's O of log n. And you might wonder then, well, what if we sort this array? If it wasn't sorted to begin with, is it more efficient then to do a binary search, sort and do a binary search, or do a linear search? And the answer is that it is more efficient to do a linear search, because sorting in itself is at minimum n log n. This is like the fastest algorithm for sorting that there is. And you can't really go beyond this. So I will also say that the whole big O notation deals with the worst case scenario. So obviously, if you're starting with a very sorted list and you try to sort it, you might sort in very little time. It doesn't necessarily have to go to even n log n, but this is the worst case scenario. And you want to basically have your algorithms, if you have an algorithm and it's an O of n algorithm, then that's a fairly good algorithm, I would say. There is one sort that is actually O of n. It's actually not O of n, but it looks like an O of n algorithm, and it's this one. I don't know if you guys have ever tried this. This is I got this from Kevlin Henney, and I think it's a pretty cute sort, where you try to sort a list of numbers by basically delaying the printout n seconds based on what the number is. Now, this is an O of n. Is this a very efficient algorithm? Not really. So again, O of n, or like this big O, doesn't tell the full story, but it tells enough of a story that it will take us and that we can compare. So one more thing about O of n before we leave. If I want to look up a fruit in this list, that's going to be an O of n thing. So I have to basically go through the full list to figure out if the item is there. But if I make this into a set instead, a hash set in C# or a dictionary or anything that uses hashes and keys, then I will look it up by key in O of 1. So this is quite important, because if you don't think about anything else about algorithms, then just knowing that if you want to do keyed lookups, you're much better off with a hash set, which is a key lookup type structure, versus a list. And that will make a lot of difference for you when you go through things. So let's take a look at another data structure instead of hashes and lists and things like that, a graph. So graphs are insanely useful, but they're also a little bit scary when you start out, I think. So graphs can be used for modeling a lot of things. Like natural things that you will model with graphs are like relationships, like Facebook, friends. This is an undirected graph because every relationship in this case is bidirectional. If I'm friends with someone, they're friends with me back. If we're looking at Twitter, for example, this is a directed graph because I might be following Beyonce, but she's not following me back. So maybe, no, I don't think she is. And then you can model, for example, in this case, we're modeling cities. as a graph. In this case, the nodes, we'll call them nodes or vertices, are the cities, and then the things in between are called edges, and there are the roads in this case. And you can also see here that we have weights on the road. So it's a different thing, and like it's faster maybe to go from this city to this city, that's like 30 kilometers, versus going here is like 70 kilometers. So it does make a difference which road you take. So that's like a weighted graph, and this graph also has a cycle. So it means that you can go around in a circle and end up where you started. That's quite important for these algorithms. This one is like a similar one with weights, but it's got like two different groups. This is generally called a disjoint set. And then you can model other things like graphs. Like let's say you have a matrix. In this case, all of the spots that you can be on in the maze are nodes, and all of its neighbors are the other squares that you can get to. So in this case, the neighbor of the starting square would be this square. And instead of like actually modeling the graph from the start and putting out like all the different edges, you gradually generate these edges as you go along. Similarly, if we have like a horse, in this case, we have the same matrix, and the horse is the starting point, but now these are the neighbors. Like the horse cannot move is to its adjacent squares, but you figure these out as you go along. So we have other types of graphs, like a tree. This is a special graph. You use the same kind of algorithms and everything for it, but you can take some shortcuts because you know it's always going to be like going from the root. Every root's going to have, or every node's going to have two children, etc. You can have a binary search tree. This is a very useful structure for doing things in the same fast way as binary search. So in this case, if I look at number 7, I will know that it's always going to be to the left of the root, which is 8, because it's smaller than 8. And that way, it makes it incredibly fast to search through. One of the trees, there's also an important tree, it's called a trie or prefix tree. So this is something that you can use, for example, let's say you do routing on the web. And you want to know as people type something in, or even if you're doing autocomplete, you can do something like this to figure out if a string is valid or not. So let's say I start typing in A. From the root, A is a valid letter. It's in the list of places I can go to. I type in P again, and now I've reached a point where that node is marked as being an end letter in a word. So I will know as I type that app is now like an actual word. But app is also the start of apple. So if I continue and I write L, I'm now not at a word, but I'm at a valid path. And then I go to E, and I'm at a valid one again. But if when I was at APPL, I would have typed Y, well, Y is actually that. I would have typed X. I would have ended outside of the tree, and it would have known that, okay, from here you cannot go to a valid location anymore. So this is a very useful tree for when you want to do prefix searches. So if you're thinking about like routing in ASP.NET, this is what you could use to figure out if the routing is ever going to be correct or not, or if you can shortcut and say, I'm not even going to bother with this route. And then another graph is a linked list. I'm not going to spend too much time on that. But if we have a graph, they look pretty on paper, but how do you actually represent them in code? So one way that you can represent them is by doing an edge list like this. So in this case, this edge list actually fully describes this whole graph, assuming that it's a non-directed graph. It's not a very efficient way of describing it for algorithms, but it's a very efficient way for describing it because of its brevity. You can also put in things like the weights, and it works very well. But a more efficient way to describe it for algorithms is like this. You instead describe every node and all the other nodes that you can get to. And this is called an adjacency list. So typically when you have a graph problem, you will represent it maybe initially as an edge list, but then immediately kind of transfer it over to this adjacency list format so that you can go through and run algorithms on it. The reason why this is more efficient is because if I wanted to look up like any nodes that I could get to from Oslo in the other case, I would have had to look through every single edge and seen, is Oslo part of this? And then which is the other one? And this is how you would represent sort of like a weighted list. But enough about data structures, even if data structures are fun. Let's look at an algorithm, and this is like a base algorithm for graphs. So we have two basic algorithms for graph, BFS and DFS, depth first search and breadth first search. We'll start with the depth first search. And what we do in here is we start with one node, and we then go to its neighbor, and 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 so on, until we reach the end. Or if we don't reach the end, we will then go back to the last time a node had more than one neighbor, and then go on sort of the other path. So this is a quite easy algorithm. We also use a visited set to avoid doing cycles. We don't want to kind of like go through and go down and then happen to go right again, because that would put us in a cycle. But this is an easy algorithm to remember. You just, put, like you have this last in, what's it going to be? Yeah, last in, first out queue. And just kind of process them until you have nothing else to process. Unfortunately, if you see in this, you can see that we missed a path to the end that was just 4 squares, where we found this longer path instead. And that's going to happen if you're doing DFS. DFS is not a shortest path algorithm. But what we can do instead is we can replace this stack or this LIFO queue with a FIFO queue. And if we do that, we'll end up with this. So I go through and I start at the man again. I put in all its neighbors. And then instead of going to its neighbor, I'll say I'll go to all your neighbors. And then we'll go through all this level's children and go to all their neighbors and all their neighbors. And this way we can actually secure that we're going to get to the first, this is going to be the shortest path to the end. Now we're doing this in a matrix, but this works in any kind of graph. So BFS, like literally this, if you've done this a few times, you can write this up in your sleep. Like it's a very efficient, but also very understandable algorithm, I think. And very, very useful. So let's use this in a very different scenario. So I'm not sure if you remember this problem. I'm sure some of you do, the die-hard jug problem, where you have 2 jugs. One is like 5 liters and one is 3 liters. And you want to end up with 4 liters in one of these. You can't like fill them up, even though they have numbers on them. You can only fill them up to the rim, and then you can pour things over to the other one. So what we can do to solve this problem and end up with 4 liters in one, we'll start off with 5 liters. We'll pour it over in the other one. Now we have 2 liters in the first one. We'll then pour it out, or pour it over, get another 5 liter, end up like this. And now we end up in a state where we have 4 liters in the big one. So what does this have to do with graphs? Anyone? No one sees a connection between this and graphs. OK. What if we do something like this? We mark these as states. Like it's pretty easy to see how we can mark these as states. And if we do this, like each of these are now nodes, and all the things that you can produce from that state, you can, like, so if you have 5, 0, you can go to, for example, you can throw it all out and have 0, 0, or you can fill up the 3, so you can go to 5, 3, or you can pour over the 5 and the 3 and go to a 2, 3 state. So you can calculate the next state, and you can make a graph like this. So in order to solve this problem, you can use graph algorithms, and this is like a very, very common way to use graph algorithms, where you use states as the nodes, and use the transitions, which you can calculate all the time as the edges. In this case, we just take the shortest path to any state that has 4 in it, and we're done. So graphs are much more powerful than just whatever you can draw as a picture. If we're doing shortest or cheapest path, we already talked about breadth-first search. If you have something like this, where you have a matrix, but in this case you have to pick up a key before you reach the end state. In this case, your state for the node would not only be the node itself, but the node plus whether or not you also own a key. So it's okay to go back to an old node, it's an old square, as long as you go back only if you're in a different key state. So like each node would be x, y, plus a Boolean, key or not key. And then you can use BFS again. So this is also a very normal thing where you denote it like as a state like that. Or if you have a weighted edges, you might have to use another algorithm, like Dijkstra is an algorithm that's frequently used. And the reason for this is because even if you take one road, there might be a faster way or a shorter way by taking 2 roads to the same location. So the number of steps or the number of roads does not denote like how fast you will get there. Like the sum of the length of the roads will do that. And then you have other algorithms that are interesting. So A* is another very similar algorithm, but the thing it takes into account is that you have some heuristics. So let's say I want to go from London to Edinburgh, then I'm not going to take, I'm going to say a heuristic to say I'm always going to pick, maybe, I don't know, take north roads, for example. Always go north, because that's going to be probably faster to get there than if I would just take any road. But with something like A*, if you have a bad heuristic, you might end up worse than if you didn't do A*. I'm going to just do one more algorithm on graphs before we leave it. And this is something called a topological search, which is also a very interesting type of algorithm. There are plenty other algorithms on graphs, and like union find is one if you want to look that up. But course schedule, what we want to do is we have a graph that looks like this, where you have to take class 0 before you take class 1 or class 2, and you have to take class 1 and class 2 before you take class 3. Like they're prerequisites. And you want to figure out in which order should you take these classes in order to end up well. So the 2 options here are 0 will always come first, and then either 1, 2, 3, or 0, 2, 1, 3. Both of these are as valid orders, right? So how do we figure out this order? This is actually one of the cases where you might end up with multiple solutions, but either way, both of them are fine. So one way to figure out like this topological order is to use something called a topological sort. And this is a super easy algorithm. It goes like this. We look at any node that isn't a prerequisite for anything else, in this case 3. This is going to be at the end. This is one of my valid end nodes. And then we take away anything pointing to it. And now we're looking at whatever else now isn't a prerequisite for anything else. And we'll put them in here. And now we suddenly have 0 that's not a prerequisite for anything else. So this is now our order. Our order in reverse, but still our order. It doesn't really matter. Like reversing is a simple thing. So this is a very useful algorithm for when you want to know, when you want to order anything like this. One of the things we did here was use a visited set to avoid going into a loop. And that's kind of like a little bit of caching, which takes us to another set of algorithms that are extremely powerful. It's called dynamic programming. Dynamic programming, I felt when I kind of started reading about algorithms again, that people were kind of like flashing this dynamic programming. I'm so cool, I'm doing dynamic programming. But it turns out dynamic programming is just another way to say caching. And caching, I don't know, all of us do caching. I don't know how cool you feel when you're doing caching. But we're going to look at, anyways, how you can use this to greatly speed up your algorithms. So, everyone is familiar with Fibonacci, I guess, I hope. Fibonacci numbers is like you get a Fibonacci number by taking the previous plus the previous Fibonacci number. If we look at how we calculate, for example, Fibonacci of 5, we know that it's going to be Fibonacci of 3 plus 4. But then, if we look and we expand the tree a little bit, we'll see that we're doing a lot of duplicate work. Right? We're calculating Fib3 twice, and Fib1 also twice, and Fib2 actually we're calculating it 3 times. So if we're doing like Fibonacci of 1,000,000, then obviously we're pretty fast going to run out of computing power on our machine. And I'm sure you've done this, and I'm sure you, even at Fibonacci 50, like it gets mad. So one thing we can do is we can do something called memoization. So memoization is also just another word for caching. So what we do is we just basically save the results of our Fibonacci sequence. We don't actually recalculate it. So we do this. In fact, in languages like Python, we don't even have to do this. We can just put the @cache directive at top, and it does the memoization for us. So if you're ever doing this kind of recursion, you're in a language that allows you to just put the directive, do it. If not, cache by yourself, it's not a big problem. What we need to remember, though, is that when we're doing something like this, we're also kind of like, we're getting speedier, but we're also sacrificing memory. Because we have to store the data somewhere, so we're actually going to we're trading off memory over speed. And in order to be able to cache, we also need to have the inputs, in this case n, be hashable items. So ints, strings, something like that, but they can't be lists or objects, so you have to kind of like transform them in some way. So that is something to remember about just what parameters you can use in a case like this. But this is very easy. There's another way to do dynamic programming. It's called tabulation. And tabulation is basically, instead of going top down, you go bottom up. So in our first case, we said fib of 5 is equal to fib of 4 plus fib of 3. In this case, we're starting at the bottom, and we're saying fib of 0 and fib of 1 are these numbers, and then we calculate 2 based on them. So we're just basically creating a long list of, from the very start, from 0 and on, these are what the numbers are going to be. Whether or not you're going to use tabulation or memoization depends on, for example, if you're actually using every one of the numbers, 0, 1, 2, 3, and so on, to calculate maybe 50, it makes sense to do tabulation because you don't have to do recursion, which is expensive. Whereas, for example, if you have something where you're just sparsely using the other values and you don't know which other calculations you'll use, then memoization is a better option. It's just a trade-off, but both of them are useful. So let's see how we can use this in a real case. I don't know, maybe not super real, but this is a case of a house robber that is robbing houses, and he has this special thing where he will rob a house, but if he robs a house, he will then not rob the next house, because then the alarms will go off and he'll get caught. So let's say he could rob, for example, 1, 3, and 5, or 1, 4 would be an option, or 2 and 5, or something like that. So how would we figure out how he could get the most loot out of this? One way, the brute force way, would be if we set up all the different options in here. Actually, I did have another slide that was like a little bit better for this. Okay, here we go. So these are all the options of like where 1 denotes that he could do the robbery and not. Except for we have to remove the ones where he's robbing adjacent houses, and then we would calculate the loot. So everything that was left, we would just go through and calculate, and we'll take the max of that. Sounds like a good plan until you realize that, in the test scenario you had like 100 houses, which would mean that we would now do 2 to the power of n times n, which means like 127 times 10 up to the power of 32. This is me waiting for that to finish, doing this brute force method, until I realize that I know dynamic programming and I don't have to wait for that to finish, because we can do this more efficiently. So if we look at this again, and we say at every single house, and this is a very common pattern for dynamic programming. So dynamic programming works well if you have sub-problems that are repeatable. Like in the Fibonacci case, we often did Fibonacci 3, Fibonacci 2, and we can cache them, right? So in this case, we go to house 0, and we have 2 options. I can rob it, but if I rob it, I cannot rob until I get to house 2. Or I cannot rob it, in which case I can rob at house 1, right? So this is how our equation actually looks. The maximum loot at 0 is taking the loot plus getting the maximum loot at 2, or not taking the loot and getting the max loot from 1 on. Now, can anyone see a pattern here? This looks very much like the Fibonacci sequence, where we're actually just doing like, we're relying on two previous equations, or 2 previous runs of this. So given this, we can basically just write this piece of code, cache it, and now this is actually an O of n solution. So instead of 127 by 10 to the power of 32, we're doing 100 operations. That is a big saving, and this is something that I frequently actually use at work, for my code at work. So I quite often use this cache directive or this type of memoization, even though it kind of like has gotten a little bit of a leet code type connotation to it. Make sense? Yeah? So we're going to look at a different type of algorithm, but that's a subset of the dynamic programming or caching algorithms. So what we have here is a sliding window, which I'm sure that you're all kind of like at least familiar with the set, that we're going to look at like a small piece of maybe an array or something like that. So let's say we take this. So we have an array, and we want to know the maximum sub-array of size 4. By maximum, I mean where the sum is maximized. So it's an optimization problem. So one way that we could do this, the brute force way, is like this. We'll look at this, sum them all up, it's 2. We move on, we sum them all up, it's 51, and so on, and so on, and so on. So this is normal way, and it's, small arrays, not a big deal, small subsets, not a big deal. But do we see a pattern here where there's like a lot of yellow in the middle, which very strongly indicates that this is a repeating subproblem, like where we're actually doing the same calculations over and over and over, so we could be speeding these up. Anyone has an idea how we could speed them up? Well, I'm not going to put you on the spot. But this is the way we could speed them up. So in this case, we would have the actual times we would run would be n minus 4 times 4. This is like the O of that we're running with. What we could do is this. We calculate the first one, which is 2, and then we take that calculation. So we take the 2, we just remove the one that we are not using anymore, add the one that is now a part of our list. So we're constantly reusing this, like this calculation that we previously did. Now, you might look at this and say, well, you know, you're doing 3 calculations instead of 4. I am not very impressed. But what if the sublist was not 4, but the sublist was like 100? Now we would be doing 3 calculations instead of 100. Because instead of summing up like the 100 items every time, I would just be removing the one I left and adding the one that I'm tacking on. And this is sort of like the sliding window thing, because now we're talking about an O of n algorithm, where we're only ever touching each object once in the list, or a constant number of times. So very, very useful. Let's see if we can apply this to a problem that sounds a little bit more complex, maybe. So we have this bookstore owner, and he has a number of people that come in to his bookstore. These are the number of people that come in every minute. Depending on if he's happy or not, they will be happy, and they will buy things. So he's sometimes happy, sometimes sad. So these people that are marked here, they will buy things. Now, he can do something, maybe take a pill or something, and he can be happy for 3 minutes at a time. And the question is, when should he optimize to do this? Now, translation, for me working in Azure Batch, like I have, I don't know, a rebate that I can only use for like an hour each day or something. When do I apply that rebate? That's like a typical scenario in a real world situation. But the question is, how can we do this, and how does this apply to a sliding window? Well, we can do this. We know that these people that came in when he's happy, independently of like if he had like this extra special happy power, they will always buy stuff. So we can take them out of the equation, and now this does become the same problem that we just looked at, where we do a sliding window of 3 minutes and see which sum is maximized, which happens to be this one. So we use the exact same algorithm as we did before, with removing and adding. And we end up with this. So this is, like on LeetCode, this is a medium problem, but in reality, when you've looked at it and when you dissect it, it becomes like a fairly easy problem. It's just a matter of kind of like cutting out and separating the pieces and applying these base algorithms to them. So we'll look at one more sliding window problem. It goes like this. So this person, or let's say her name is Mona. So Mona likes fruits, but she can only ever have 2 types of fruits in her basket at any point in time. And she wants to pick fruits of every tree. And the question is, how can we maximize the number of fruit that she can take? Visually, we can just see here that the answer is going to be 4, like apple, orange, orange, apple. But how do we do this programmatically? And this is a little bit of a different sliding window, because here we have a grow and shrink technique, as you'll see. So what we'll do is we'll start off with the apple. We'll take the orange. We're still good. We only have 2 types of fruits. Orange, still good. Apple, still good. But what happens now when we get into the pear? Now we don't have a good state anymore, so now we have to reduce our window until we do have a good state. So now this is a grow and shrink window where we do this and we can expand it. We get to 3, we get to the orange, we have to reduce it back again And this is kind of like a technique that you would use also that's an O of n algorithm. So whenever you can use like these sliding window algorithms, which is basically optimize anything over a list of things, is typically a sliding window problem. So those are the two main cases, like a fixed length or a grow and shrink type situation. This one is like a little bit different, but I'm still going to bring it up because it's kind of like a sliding window, except for we're going to shrink from the edges. So what we have is a list of walls, and we want to, I don't know if you can see, but this is supposed to be blue. I realize now that it's not very, you can't see it super well. But so the walls kind of trap water in them. So if we take the two outer walls, we can trap 8 units of water, maybe 8 cubic meters or whatever it might be. And now the question is, given what two walls can we maximize the amount of water we can trap? We can only trap it, based on like the lowest wall, the lowest edge wall. So how do we make this, how can we possibly get any better than 8? Well, we can't get any wider. So the only way we can get better than 8 is if we go higher. So we can say, from the 1, shrink it in and take any wall that's higher than 1. So we'll go to the 8 wall, in which case we now have like a height of 7 and a width of 7. So this was obviously a lot better. And then the only thing we can make this better would be to get higher than the 7 wall, which is our lowest wall, which would go here. It didn't happen to be higher, but it could have potentially been higher. And now we have 2 equal walls, so we can take any of them and shrink it, and we'll see that we'll get 0. So these are like our options. And again, in O of n, we solved a problem where otherwise we would have to brute force and look for all the combinations of walls out there. So this is a little bit of power of these sliding windows. Okay, so we're getting a little bit to the end. We're going to look at how you kind of come up with which of these to use, or like how you can maybe think through a problem. We call this the algorithm of an algorithm. The first thing that I do when I go through these is I try to ask a lot of questions. I try to ask, the limits, the boundaries, what is it I'm actually trying to solve. And I find this to be, well, I'm sure you guys also feel like this is something that's super important in your day-to-day jobs. As an example, just yesterday I was working with one of my colleagues, and we were talking about we needed to get some statistics out for how many tasks were running in batch and at a certain time. And he was looking at it as in searching out all the tasks and then counting them, while in reality, you don't actually have to have all the tasks. You only have to have the count of the tasks. So I went about it instead and looked at the statistics, which turns out to be a much cheaper operation than to get out the full list. Why I'm mentioning this is because this is also true for when you're looking at these kind of algorithm problems, that you need to look at exactly what it is they want you to do. Oftentimes, people end up simulating an entire kind of an entire scenario when there is, if you look at the patterns, you will notice that there might be a mathematical equation that can solve it, or there might be something like that. So it's very useful to ask a lot of questions and look at the limits. And if the limits are in the cocoa and banana case, you can see that it's going to end up in the trillion case. That is almost only feasible for something like a binary search or the divide and conquer algorithm. You're never, even O of n in that case is going to be too much. So then almost immediately you need to resort to that. That's not a really a real-life thing you can do, but like when they have like prepared tasks on leet code and things like that, you know that if they have that big of a boundary, it's going to be a binary search issue. Then what I like to do is I like to draw a lot. And I like to kind of like think out all the examples. So even like, let's say in the cocoa eating banana case, I would go up and type up, like, write down like what the different things look like, because once you kind of start drawing them, and especially if it's like a visual problem, like you can maybe see here in my notebook, you'll start finding these patterns, because it's like you have this funny thing where if you start doing things manually and start kind of like without having to think about how exactly do I get to this point, maybe I'll start picking out, like the lowest number of the list. I don't have to worry about how I find the lowest number of the list, but mentally I can pick it out. Then at least make that a part of my thing. But you find patterns, and that kind of becomes this like, oh my God moment where you now know that this is like you're onto something that you can start work on. Or you start finding a pattern that would lend itself extremely well to binary search or to a graph, or like you start drawing them out in different ways like that. And then I like to kind of like split the problem up into very small pieces, and this is something I do frequently at work too. I often write a lot of pseudocode before I even write any code. Because anytime I start writing real code, I kind of locked into an implementation, which I haven't done as long as I'm just writing, sort, I don't know, find the smallest number and things like that. And then I also have pieces that I can later optimize individually. And only then do I start implementing. And this, I mean, for an easy problem, this might be like a minute. For a hard problem, this process might be like 30 minutes before I even start writing something in code. And then I test. This when I show you kind of like a small trick for if you're doing leet code style problems. Oh, never mind. Like, I don't know if I want to actually change it. Let's see. Never mind, it wasn't super important. But I write my tests in line in the code, and that works really well for a language like Python, where you can do, like at the bottom of your code, you can do an assert and just pull it out like that. But even in C# now, you can kind of like pull in and do the test cases in your minimal APIs or things like that. I wouldn't recommend that for real work, because that's like you want to structure your code, but for these kind of like programming puzzles and things like that, it's very useful to be able to have them where the code is, so that you can easily change the code and try other more optimal versions. And then you go around and you act, well, now I've put myself in a position where that doesn't work anymore. Here. Yeah, then you go around and be happy, and then the last thing I do is I try to kind of do it in as many different ways that I could. Like I try to kind of like stretch my mind to solve it in a different, even if it's the worst way, because sometimes you'll just find out like another key insight when you're doing that. Sometimes I'll even talk to like ChatGPT and have it solve it for me, and even if it can't solve it, it might give me like another insight about how I should start. So that is my algorithm of an algorithm. If you are interested in this and you want to go and kind of like just practice your algorithm skills, I'm sure you're all at least vaguely familiar about leet code. They have daily leet code puzzles that you can go through in all ranges, easy, medium, hard, and they're free. Like you can actually buy a leet code subscription, but you can do a lot of things with the free version. And they have leet code competitions, and they're not the only one who have these, like HackerRank or CodeChef and lots of other places too. But these competitions are quite nice because they have like a weekly and a bi-weekly in different time zones. But you don't actually have to let anyone else know that you're competing. No one will, and you'll do it like from your own home. And if you fail, it doesn't really matter. No one else is going to know. What they do is like they give you 4 different challenges, and you have to solve them as fast as possible. And based on how fast you solve them compared to the other people that were in the competition, your rank goes up or down. And you can also do them outside of the times that they have set as virtual competitions, which means that your rank won't change, but at least you can try them out. And I think this is like, for me, this is like super inspiring. I don't know, did anyone here do Advent of Code? Yeah, plenty of you. If you haven't, then I do recommend going back and doing sort of like, there is years from 2015, so every December, Eric Wastel, who's doing this site, he's coming up with like 2 challenges a day for 25 days, and they're usually pretty funny and interesting. They're a little bit different from leet code puzzles because you don't have to stretch, like you only have one set of inputs that you have to fix it for. So sometimes you can create like very input-specific problems, but that's it. And then if you're interested in math more than the coding challenges, this is also a coding puzzle type thing, but very much more focused on math, Project Euler. So I do recommend go out and do that. And with that, I want to thank you so much for taking this early morning on Friday and hanging out with me in the world of algorithms. I hope to see you out there. Thanks.